All right, and welcome to chapter 10. Now, in this chapter, we are going to shift gears a little bit and talk about homolytic bond cleavage with radical reactions. In chapter 10, we want to just do a couple of things in this chapter. We'll still see some omits, but let's start with section 1 here and just talk about what a radical actually is. You've probably heard the term free radicals before in terms of looking at biological systems. Radical reactions can occur. We'll talk about that in class. In this video, we're just going to be able to talk about what the functional group or the intermediate of the radical looks like, what's the three-dimensional shape, and be able to talk about some of its reactivity in basic synthetic organic chemistry. We'll get into the real-life applications like polymerization and free radical oxidations, antioxidants, things like that in the classroom. Free radicals form when bonds break homolytically. And if we remember what that meant was that there was a single barbed or a fish hook arrow, and that's one electron moving at a time, one electron going to each atom. And so what we got were these atoms with these dots on the side. And if we remember our Lewis dot structures, that dot represents one electron by itself, one unpaired electron. That's what a radical is. It's an element that does not have a charge, but has an actual electron by itself in an orbital. Now, a double barbed arrow shows the movement of two electrons. That's what we had done before. In this chapter, we are going to be moving one electron at a time. So there's a little more arrows in our reaction mechanisms, but we have to move them one at a time because we are going to be doing homolytic bond cleavage. Now, if we remember our intermediates before, we had carbocations or carbanions. The carbocation is an sp2 hybridized carbon with an empty p orbital. That +1 charge tells us that we have an empty p orbital on that specific carbon center. A carbanion was a filled sp3 hybridized orbital. And so that carbanion was usually reactive, such as a base, such as the acetylide ion. We have an sp3 here just to show you the typical carbanion. A radical is somewhere in between. We are going to call it sp2 hybridized for this class. We are going to see it's more like a trigonal planar intermediate than a shallow tetrahedral or trigonal pyramidal. But it is more planar in nature. What that means for us is when this reacts, again, this can react from a top side to single barbed wire or from the bottom side when it's going to attack something. So racemic mixtures will form when we make chiral centers here. So just be aware of that. Anytime that we see a racemic mixture form in a product, if the radical was an intermediate, handle it exactly the same as you would a carbocation. Racemic mixtures will always form with our radical intermediates. Now, radicals are a little bit different than carbocations for sure. They are neutral charged, meaning they do not have a formal charge, but they do have an incomplete octet, and that is what makes them reactive. So just like the carbocation was a carbon with a +1 charge and was reactive because it had that +1 charge, a radical is still reactive even though it does not have a formal charge. The reason why it is reactive is because there's a carbon with an incomplete octet. We see that radicals follow the same trend as our carbocation stability. Methyl radicals and primary radicals are very unlikely to form. A secondary is better than a primary. A tertiary is more stable than a secondary. Tertiary being the most stable out of this group until we get to, you guessed it, resonance. The allylic or the benzylic position of a radical, just like the carbocation, is resonance stabilized. And so when we see that resonance, we have to be able to talk about the delocalization of that single electron, that lack of an octet. Even though we are not delocalizing a formal charge, we are able to delocalize the actual lack of an octet here across that radical molecule. Notice here the single barbed arrows. One electron from the radical is going to be shared with one electron from the pi bond. The other electron from the pi bond is going to become a new radical on the other terminal end. I'll call that carbon 3. So it is very important to be able to draw these resonance structures, as we see that resonance is the absolute best stability for a radical. We're looking at bond dissociation energies here. Now, what does decreasing bond dissociation energy mean? The lower the bond dissociation energy, the easier the bond is to break. And so what we have to be able to think about is all of these carbon to hydrogens are being imagined to break homolytically, right? Just imagine that is what the bond dissociation energy means. We took this bond and we broke it homolytically. The lower the bond dissociation energy, the easier that is to break, which means that this resulting radical is stable. So the radical is stable if the bond dissociation energy is small. It means it doesn't cost much to break it. So we do see the resonance radicals are the easiest to form. And then our tertiary radical, our secondary radical, primary radical, and our methyl radical. That's the same stability we saw before. We're going to add in this vinylic radical, right? When we think about that carbon that is already sp2 hybridized, pulling off that hydrogen in a homolytic reaction would result in a radical on an sp2 already hybridized center. So then you're thinking it's sp hybridized because it has two p orbitals, one for the radical, one for the pi bond. This is very unstable. Just like we saw in the alkyne chapter, the triple bond chapter, vinylic carbocations were extremely unstable, and we do not even think that they form. So looking at these values, we can start to realize that the easier something is to break off homolytically, that results in a more stable radical product after that reaction. Couple of different patterns, just like we've seen patterns before in heterolytic reactions. We're going to talk about these homolytic patterns as well. Klein has a very nice chart in the textbook, which we'll be filling in right here with the mechanisms. So let's follow along. Homolytic cleavage, usually initiated by heat or light. You can initiate them with a peroxide as well. We'll talk about peroxide initiators a little bit later on. What heat, light, or peroxides do is it will start by homolytically cleaving the bond. Right? One arrow for each electron, one electron for each X element there. Addition to a pi bond is another radical mechanism pattern. Notice here the addition of the pi bond is going to be creating a new sigma bond between carbon 1 and creating a radical on carbon 2. A couple of things just to note, these two arrows, I'll highlight them in green, are making the new sigma bond from the pi bond, and carbon number 2 gets the leftover electron as a radical. That radical right there. Hydrogen abstraction, it's not the same as a proton transfer because here we are not doing heterolytic cleavage. We're not actually transferring a proton, an H+1 cation. We're actually transferring a hydrogen, right? So a radical can come in and swap partners with that hydrogen. Notice one electron is going to carry from the HR bond to the X radical. That makes that new bond, and I'll try to color code here. The leftover creates the radical on R. Halogen abstraction is very, very similar. A radical can come in and make a new sigma bond with X, which would be in this case a halogen, and a new halogen radical is formed. These patterns are very tricky. We're going to practice them in class simply because our hands are used to heterolytic cleavage, and now we're trying to push one electron at a time with homolytic cleavage. Just a few more. Elimination, which is the reverse of addition, which was our second pattern in the previous slide. Elimination is still creating a pi bond. Just like in addition, we react a pi bond, elimination is still making a pi bond. However, we're doing it homolytically now. So when we look at this elimination, what's really important to note, again, I like to count my carbons. We are going to make a pi bond by sharing a radical from carbon 2 and one electron from the sigma bond on carbon 1. The rest of the sigma bond is going to make that radical on X appear. So we can make new pi bonds via radical elimination. Coupling is the reverse of pattern number 1, homolytic cleavage. Coupling is bringing two radicals together to make a new sigma bond. Now with these patterns, they're going to be put into one of three categories. And these categories are what we are going to see as our radical mechanisms in this chapter. So not only do we have patterns, but we do have categories in our mechanisms now. The three steps or the three classifications are initiation, termination, and propagation. We usually start with an initiation, then followed by a propagation. We want to make our actual reaction, make the organic product. That happens in the propagation. And then there's also a termination step. These two involve making radicals, or what we'll call quenching radicals, using them up, right? Initiation will make them, termination will finish them. Propagation is where we actually do the organic reaction that we want to. So to start us off, an initiation step is one where radical species are formed by non-radical species. So see here how we have one molecule and we are making two radicals from that one molecule. An initiation step will always involve the pattern homolytic cleavage, pattern number 1. Now, when we're looking at propagation, this was all that middle section that we just did in the patterns. Addition and elimination, hydrogen abstraction, and halogen abstraction. It occurs when we have one radical plus one molecule in the reactants, and then we make one molecule and a new radical in the products. All of these involve that. There's a radical in the reactant, there's a radical in the product. So it's a propagation. Keep the reaction going, right? Finally, our termination is going to involve a coupling reaction. It actually is where we have two radicals coming together to make one molecule. Notice how there are no radicals in this final product. It's the ending or the termination of the actual radical reaction. Let's talk about halogen thermodynamics. Let's get started with getting specific about our first radical reaction. Notice here that we are going to be talking about thermodynamics. Thermodynamics is going to be very important for us to understand what is happening based off of our reaction. Now, halogenation, overall reaction here, is going to be a substitution. This substitution reaction involves substituting a hydrogen for a halogen. So notice we have CH4 here, just a very simple organic molecule. We are taking that CH4 and making it CH3X. Now, typically for halogens, we've worked with Cl2 and Br2. We are going to be doing the exact same thing here, but we want to make sure that we understand the difference between chlorine diatomic and bromine diatomic. Now, notice in this overall reaction that we have a couple of things going on. We have bonds breaking. We are going to be breaking the CH bond and the diatomic halogen bond. We are making a carbon to halogen bond and an H to halogen bond. So there is some enthalpy going on here, right? Delta H equals bonds broken minus bonds formed. The entropy term is going to be negligible for us. We don't really care about entropy here, because if we look at the actual reaction, we have two molecules making two molecules. So entropy is going to be 0. Now, when we look at the reaction itself, what I want to present here is the mechanism. We need an initiation, a couple propagations, and a termination. We're going to follow this cookie cutter type mechanism. It's a slight change of what we're used to. However, radical reactions are different in that their homolytic cleavage requires a different style of mechanism. The first thing that we need to be able to see is that homolytic cleavage. We'll see that the halogen bond, X2, is going to homolytically break. We do need heat or light, either one. HV is light. If you imagine energy equals H nu, delta is heat. We need one of these. They are our radical initiators. So X2 will not just homolytically cleave without a specific H nu, light, or delta, heat. Once we make that radical, we can go straight to our propagation steps. In the propagation step, we will start with hydrogen abstraction. A hydrogen off of our organic molecule will combine with the halogen. There makes that new bond, followed up with the formation of a radical on the carbon. This is hydrogen abstraction, because the halogen is taking the hydrogen away. The radical is taking the hydrogen. Next, we will have a second propagation step to make our second molecule, the actual organic product here, where we have halogen abstraction. The carbon radical will pair up with one of the halogens in a second equivalent of X2. This propagates and makes a second equivalent of halogen radical. So we are making a new bond and making a new radical in this halogen abstraction. That completes the two propagation steps for this reaction. So then we would wrap up this mechanism with a termination step. Any two radicals that you have seen in this mechanism, they could be carbon radicals or they could be halogen radicals, can come together in this coupling reaction. I'm choosing the halogens to come together because they are the simplest to write. And so why not make life a little bit easier for ourselves? Here is the overall mechanism for halogenation. Whether you are using Cl2 or Br2, the reaction mechanism is the exact same. We have to consider thermodynamics though, so that's what we're going to do next. Which one, chlorine or bromine, reacts faster? Which one's slower? Mechanistically, they are all the same. Kinetically, they are quite different. Here's some thermodynamics for us. This chart is a good explanation of bond breaking versus bond forming that we just talked about. We can estimate the delta H, the enthalpy term, based off of the bond dissociation energies. We know bonds broken minus bonds formed. Here are all of the different types of bonds relevant to this reaction in terms of bonds breaking, minus bonds formed. Don't worry, you don't have to do the math. It's done for you. So when we look at this, what we do notice is that using I2 is not enthalpically favorable. Enthalpy here as a positive, this is endothermic. That would relate to a non-spontaneous reaction. Remember, entropy term is 0. So whatever the enthalpy sign is, that's what your Gibbs free energy sign is as well. So endothermic means endergonic, means not going to happen. Gross. Now, F2. Yeah, you're like, why not, Lauren? Come on, let's go ahead and use this. This is way too anthropically favorable. There is no way that we're going to get F2 to react this way. We choose to use chlorine diatomic and bromine diatomic because they are our superstars. They are the right type of spontaneity that we can see without being catastrophic for the actual reaction. Notice though that their delta H's are different. Cl2 has a more negative enthalpy. It's more exothermic than the delta H for Br2. So both chlorine and bromine are exothermic, which is favored. But let's look at the big difference here, the difference between the first propagation step and the second propagation step. Let's remember our mechanism. Hydrogen abstraction, the halogen will come and make a new bond with hydrogen and make a new radical on carbon. Notice the difference here between chlorine being the radical that does this versus bromine being the radical that does this. What do you remember about bromine versus chlorine as anions? Well, we know that Br minus is more stable than Cl minus. The same goes here. Br radical is more stable it's harder to react in hydrogen abstraction. And so that's some key point here to look at, that hydrogen abstraction for bromine is slower than that for chlorine. Chlorine's hydrogen abstraction is faster. It's exothermic. So we make more stable things. That's something interesting. We're going to look at the reaction coordinate diagrams in just a second. The second propagation step is very similar for both of them. Halogen abstraction, right? Making that new carbon to halogen bond. Look at these numbers, very, very similar. So when we're looking at the rate determining step, it must be that first propagation step. There's our rate determining step, hydrogen abstraction. This is the one that we want to focus on when understanding the difference between chlorination and bromination in this radical chapter. Bromination is much slower than chlorination. This means that bromination is going to be selective. That first step, the rate determining step, is either going to be for chlorine, exothermic, for bromine, endothermic. We know, same idea when we were forming carbocations. If that rate determining step is really slow, we get to be selective. We get to choose what reaction we are going to do. What this literally means is that when we start looking at the products coming out from chlorination versus bromination, chlorination is not going to be selective. It will do hydrogen abstraction on any hydrogen that we have. Bromine is going to be choosy. He's going to be selective. He's going to take his time and figure out which hydrogen is the best to remove. Which one is going to actually be the easiest to remove. Even though secondary radicals are more stable than primary, we see chlorination making multiple products. Not quite racemic mixtures, not 50-50, but definitely major versus minor, and getting multiple different constitutional isomers. And that big overarching reason is because in the rate determining step in the hydrogen abstraction, the transition state difference is very, very small. There is a small difference in energy here. And so either radical will technically form, right? Yes, the secondary carbon is faster than the primary, but what's of utmost importance to note is that chlorine is not selective. We will make more than one product. Chlorine can go on any position out of that organic molecule. Notice that we're only showing carbons 1 and 2 here because propane is symmetrical. Carbon 1 is the same as carbon 3, right? Taking that a little bit further, we see the same propane molecule and we see a 97% product from the secondary carbon. This can't isolate that. We're going to assume that that means it's not formed as an actual product. If I can't actually isolate it, if I can't extract it as an organic chemist, I'm not going to ever see it in my product solution, right? I'm not going to be able to isolate it as a viable product. So bromination is slower because hydrogen abstraction is endothermic. Chlorination is much faster and not selective because the rate determining step, the hydrogen abstraction, is exothermic. The Hammond postulate will be able to explain a little bit better for us. In the Hammond postulate, we said whatever molecule, the reactant or the intermediate, whichever one was closer to the transition state is what we want to focus on. So in chlorination, the transition state is closer to the reactants. And so what that means is that the bond of the carbon to the hydrogen is only beginning to break, not really broken yet. The energy cost is not quite there yet. So any hydrogen is valid to be abstracted. In bromination, the intermediate, the radical, is closer to the transition state in terms of energy. And so therefore, we assume that the bond is almost completely broken from the carbon to hydrogen. So the bromine has to be very selective at which hydrogen it's going to remove. It's going to remove the hydrogen that is on the more substituted center to result in the more stable radical. Chlorination does not do this. And so when we see chlorination, we'll get all different constitutional isomers on our alkane starting material. Bromination is going to be much more selective for the lowest energy pathway. That means he will choose a tertiary over a secondary, he'll choose a secondary over a primary, and he would choose a primary over a methyl. Let's look at that a little bit more in depth. We have two different positions here. We have a tertiary position, and all of these methyl at the end are going to be our primary positions. Notice how all of these are the same, right? We'll call this A versus B. I'm going to erase the other B's because I think that they are understood, that they are the exact same CH3 groups. For chlorination, yes, our major product will be on A, but we will also get B's, right? This reaction actually is about a 65% to a 35%. You don't need to know those percentages, but you do need to know how to draw all constitutional isomers possible. For bromination, we will only be drawing the more substituted position. We will not get the halogen Br on any of those outer primary positions, only the most substituted. So only the most stable carbon radical gets the bromine. You can think of chlorination as another Oprah reaction. You get a chlorine, you get a chlorine, you get a chlorine, everybody gets a chlorine. All right, just a slight nod to stereochemistry. These reactions, whether it is halogenation with a chlorine or with a bromine, these reactions are not stereoselective, which means that when we have that carbon radical, we will be able to, in the hydrogen, the halogen abstraction, let's just draw that step. If we want to think about how that chlorine is being attached, I just chose the most substituted to start off. When we imagine that chiral center is formed, we will actually get a racemic mixture. Why? Because the carbon radical, we are going to assume in this class, is sp2 hybridized, trigonoplanar. So the radical could be up top, or the radical could be on the bottom, right? So when we have that hydrogen abstraction, we have two ways, top or bottom attack. So looking at our actual products here, we will make two secondary alkyl chlorides and one primary alkyl chloride. 3 products total. All right, let's continue on with section 7 here with allylic halogenation. Now, we do know that the weakest CH bond, the one with the lowest bond dissociation energy, will undergo radical hydrogen abstraction faster than others. We saw that with the bromination selectivity. And we do know that from our very beginning discussion here that the CH bond that is in an allylic position would be the lowest bond association energy. That's what we see here at the 364 kilojoules per mole. Now, the reason for that position having the weakest bond is because the radical that is resulted from that homolytic cleavage of the CH bond would have resonance and stability. So we are going to see that there are very specific reactions that alkenes can undergo with hydrogen abstraction at the allylic carbon. Now, that hydrogen abstraction at the allylic carbon, we said it has resonance stability. So let's just review that resonance structure over on the right-hand side. Remember, one arrow at a time. The radical will go and share with another electron from the pi bond. The second electron from the pi bond is going to become a radical on the top left. Let's just label these 1, 2, and 3 for the carbon so that we can see the rearrangement there, the resonance stabilizing effect. So when we think about that allylic position, we can do bromination of that allylic position, but there's a problem. The main problem with using Br2 with heat or light at the allylic position is that we actually get another product. Let's go ahead and take a look at that product. We actually get addition, right? Yes, we are using a radical initiator of heat or light. Here is written with light, but we have competition. Because there is so much Br2 in the solution, we can't make that homolytic cleavage happen for every single bromine diatomic. So we get these two different competing products. And so typically we do not like to use Br2 when we have an allylic position being brominated. Instead, what we want to use is a bromine source that keeps the amount of bromine low. So we will use NBS, N-bromosuccinimide. Notice it's one equivalent of bromine radical for every one molecule instead of Br2, which would have been 2 equivalents of bromine radical. The initiation step here for this reaction starts with the homolytic cleavage of NBS. So NBS instead of Br2 will be over the reaction arrow. We still should use heat or light. Here we have light written. So what would happen is a homolytic cleavage of that NBr bond. Notice we have a nitrogen radical and a bromine radical. The nitrogen radical is relatively unreactive here. It will not be doing any of the hydrogen abstractions because it is more stabilized. Why? There's resonance there. If we want to imagine what that resonance looks like, one of the pi bonds from the carbonyl can do resonance with that nitrogen radical. Showing this resonance just for our own purposes to be able to see how stable that nitrogen is. And so Br radical will continue on in our propagation steps. So just again to confirm, we use NBS over the reaction arrow instead of Br2 because NBS will keep the amount of bromine radical and Br2 low so that we don't have any competition with reacting the pi bond in the alkene, like what we saw in chapter 8. Now for our hydrogen abstraction and halogen abstraction in this reaction, we will see two propagation steps. The first one will be of the bromine radical coming to make a new bond with the hydrogen. Hydrogen abstraction, we're pulling off the hydrogen. The other electron in that bond will go to become a radical on the carbon. Now this is very similar to what we saw previously with our halogenation reaction. It should be very similar. The only difference is the first step when we do homolytic cleavage of NBS. Second step, we do see Br here, Br2, and I'm going to explain why. You could also use NBS to do the halogen abstraction in the second propagation step. We're going to use Br2 right now just so that we keep things a little bit simpler. This would add that bromine onto our organic molecule at the allylic position. Now the termination step is how I'm going to prove that we do have some Br2 in the solution. Remember, a termination step needs to be shown just to say that we've ended this reaction. However, it can be involving any two radicals that we want. Just to show you that we do have some bromine diatomic in the solution, I'm going to show you that there is a possibility of a termination step involving two bromine radicals to become Br2. So that's why we do see that Br2 can be used in the propagation step. You could also use NBS. It's just a little bit more complicated to draw. So feel free to use either one in the halogen abstraction propagation step. And again, any termination step can be drawn. I'm choosing the simplest ones to draw to keep things a little bit more light. Allylic halogenation with NBS sometimes produces multiple constitutional isomer products. Now, when that happens, how do we know? It's when we see an allylic position and the alkene is asymmetric, right? There's no symmetry in this original alkene. And so when we see the product, we know that this is the most stable allylic position. However, when we imagine that that first radical is formed from the hydrogen abstraction, we know that there is resonance stabilizing that allylic position. And so what we have to be able to draw is both radicals to show the multiple products that could be formed. All right, so we do have this blue radical going forward in halogen abstraction to make the first product. We could also see this green radical going forward to make the primary in the bromine or the halogen abstraction. All right, now when we are looking at that delocalization, halogenation will occur at either site regardless of stability. We will have multiple constitutional isomer products in this reaction. So we do have to take into account all intermediates. Radical addition of HBr. We saw this in chapter 9. We're going to now do the mechanism in chapter 10. I held off doing the mechanism at first because I wanted to make sure we had a very good foundation in radicals before getting to this mechanism. Now, this is an anti-Markovnikov regioselectivity. That does not mean that when we throw in a peroxide that we are going to see a carbocation appear on the less substituted center. It does not mean that we are going to see a radical appear on the less substituted center. With peroxides, anti-Markovnikov addition occurs because we are doing a radical mechanism. And so it's a different mechanism, and the actual addition of things, H and Br, are opposite of each other. And so let's dive into this mechanism. The first one, the Markovnikov addition from chapter 8, did heterolytic cleavage, where we made a carbocation on the more substituted position, and then a bromine nucleophile will come in on that more substituted position and make the Markovnikov addition product. With a peroxide, we still are going to be adding hydrogen and bromine across that double bond, doing an addition reaction. However, it's going to be via a radical mechanism. Let's dive into the initiation. The reaction is initiated by thermal homolysis, which is just going to be the peroxide originally splitting homolytically. We'll see that peroxide bond is going to break 1 electron on each side. Just in case I haven't mentioned, the arrow for that peroxide can either be on the top or on the bottom, right? So it doesn't matter where you start drawing your arrows. Either way is a-okay. But what this makes is it makes 2 peroxide radicals. And this is what's going to be going forward in our initiation step. Notice that the second step doesn't look like an actual initiation. The reason why it's hydrogen abstraction is encompassed here in the initiation is because we're waiting for the bromine radical, the radical production that will actually continue on with the organic molecule. So we're still doing a little bit of prep work here in this second step. Also, if you look over on the right-hand side, we can see that that first reaction requires heat because the enthalpy is unfavorable, right? It's endothermic for this first alkoxy radical production. So it's really that second step that is exothermic that helps us initiate this reaction fully. The peroxide radical will come pick up a hydrogen and it will make that bromine radical to carry forward. Notice here that we are going to be making a bromine radical. Never in our reactions will we ever see a hydrogen radical form. So in order to do this reaction, we are aiming in the initiation step to prepare the bromine radical itself. We'll carry that on into the propagation. Now in the propagation step, let's think about where do we want the radical? We are going to be putting bromine first onto our alkene. Notice that this is the opposite of what we did in chapter 8 with our heterolytic cleavage. Homolytic radical reaction is still generating the more stable radical. We are simply just adding bromine first. So when that bromine radical goes to add onto the pi bond, we still will make the more substituted carbon gain the radical, similar to how we saw the carbocation being put on the more substituted center. Notice that radical is on the more stable side, the more substituted side. Bromine gets added to the less substituted side. If you thought about switching it, putting bromine in this step on the more substituted side, you would actually get a much less stable radical. This is not formed. Wanted to draw it just so that you could see that secondary radical and debate with yourself. Do you want the tertiary carbon radical or the secondary carbon radical? Always choose the more stable. That's the one that's favored. Now the second step is a hydrogen abstraction. So we have an addition to the pi bond where we add the bromine, and then we will take HBr and do a hydrogen abstraction. That's going to put the hydrogen on the more substituted side where the carbon radical was. And the propagation chain will continue with more bromine radical. Let's just show a termination step, that coupling reaction of the halogens. Again, any two radicals that you see will constitute a termination step. The only radical that we have not seen, and I never want you to draw, is a hydrogen radical. very unstable, most likely never going to form. So don't do it. You can take 2 carbon radicals, you can take a carbon and a bromine radical, you can take 2 bromine radicals. You can even take 2 of our epoxide radicals. To remake the peroxide. But don't ever take a hydrogen radical in any of these steps. All right, just a little bit of understanding again when a new chiral center forms. What we want to be able to say here is that when we form a chiral center, right? Notice how carbon 1, carbon 2, carbon 1 is now chiral. Just like before, any of our radical intermediates, any of our alkenes will be considered sp2 hybridized, trigonal, planar, having a top and a bottom side. And so therefore, we do understand that this would be a racemic mixture. Notice carbon 1 is chiral, carbon number 2 is not. I do not need to show stereochemistry if I don't have a stereo center. And so therefore, we would just see these 2 products. Now for a little bit of extra fun with some real life radical chemistry. I wanted to go through a couple of real life reactions that are in your textbook. These are actual sections and the section number will be written up at the top. We'll start with section 8. Now in these sections, I won't be directly asking you for questions on these, but I find them fascinating real life applications that I feel are very important and an important aspect of this chapter. Ozone, O3, is in our atmosphere. We've heard a lot about climate change, that ozone is being depleted, and ozone is an important aspect for our environment. Why? Well, because ozone is both created and destroyed in the upper atmosphere via a radical mechanism. O3 can actually decompose into oxygen gas, O2, and oxygen radical. Woohoo, a radical. Nice. When that happens, or why that happens, is because the UV radiation from the sun is being converted or utilized in this radical decomposition. That oxygen molecule and the oxygen radical then reform to form ozone, and they combine and release heat. And so heat comes into our Earth, not the UV radiation. Ozone is an important aspect in our life. Heat is a more disordered form of energy compared to light, and so that's why it's helpful for us. UV light is a little more concentrated, and it actually can damage our skin and damage our biological processes. So we need ozone to be able to convert this energy of light from the sun into heat to warm our Earth and to warm us. This process is spontaneous because of the increase of entropy. However, ozone depletion is a serious health and environmental problem. Without ozone, the UV radiation would penetrate our atmosphere and wreak havoc on everything. One of the main contributors that is believed to be a culprit is the use of chlorofluorocarbons, CFCs. Now you can find these most often if you ever have seen aerosol cans, whether that's hairspray or paint spray bottles. These molecules, Freon, even these ones that are shown, these will reach the upper atmosphere. They're very light molecules, and so they will reach the upper atmosphere and react with the UV light to form chlorine radicals, just like what we were talking about. There is an initiation step once it reaches that upper atmosphere where there's enough UV light, and it will make a chlorine radical. Now, why is that bad? Because that chlorine radical will then go to react with ozone in a propagation step. This is very, very bad because then we make O2 and there's no ability for that oxygen molecule to react again with the oxygen radical to reform ozone. So there's no continuous process of formation of ozone. It's depleted and that's it. Chlorine radicals are formed in this step, and then the destruction of the ozone molecules will continue. CFCs have been replaced with other alternatives. These are not as harmful because they don't have chlorine, right? Chlorine radical is not produced. And so therefore they are not as harmful for the depletion of the ozone layer, but they still are acting as greenhouse gases. That's a different subject for another day. Autooxidation is a really interesting process. It's when atmospheric oxygen can form a hydroperoxide. So it's this carbon, oxygen, oxygen, hydrogen functional group. This process is usually generally really, really slow. However, it is formed with a radical reaction. Now, you don't need to know this radical reaction, but why is it important? Well, when we start thinking of these radical reactions happening, we actually see that formation of our hydroperoxide is actually one of the problems with explosives for ethers. In the lab, we use diethyl ether quite a bit in organic research. And so it actually has to be stored at a very, very specific temperature in a very, very specific canister because of the auto-oxidation that could happen. Hydroperoxides can be very explosive. And so we have to store ethers very carefully so that we don't lead to lab accidents. Also, another one is antioxidants. Triglycerides are really important to a healthy diet, but they're also susceptible to autooxidation, specifically the allylic carbons, because we know that allylic position, right next door to a pi bond, is the most stable radical. Autooxidation occurs here, and that's how food can become rancid and go bad. And so triglycerides need have a shorter shelf life unless they are preserved, right? Preservatives can also be called radical inhibitors. Now, these preservatives are used primarily to prevent the auto-oxidation reaction. How? Because they themselves can actually undergo the radical reactions instead of the fatty acid chain. So BHT can undergo a hydrogen abstraction to scavenge the radical that would otherwise initiate autooxidation. And so that's why we often call these preservatives antioxidants, because they are preventing the autooxidation that normally happens with molecules when it's exposed to air. Natural antioxidants, such as vitamin E or vitamin C, can find their way into our biological systems and be radical scavengers, so they can undergo hydrogen abstraction. Notice that when things are hydrogen abstracted, that there is more resonance in these specific positions. And so that's why they are more favorable to undergo that autooxidation or that radical mechanism instead of the typical fatty acid chain. Last one that we just want to talk about is polymerization. When we make multiple chains, this polymerization process joins together very small units. These units are usually called monomers, and they usually have an alkene with them. Now that alkene is initiated into an addition reaction, a radical addition reaction, and that radical addition reaction can cascade and make more and more connections. Now a polymer usually has the subscript here N for its unit to say many, many, many connections followed. This type of idea for polymerization is really one of the ways that we make very strong glues and also very strong plastics. Now, again, radical polymerization usually proceeds via a radical chain mechanism with that peroxide, and then the peroxide is used to do an addition reaction, very similar to what we see in the radical addition of HBr. But here's where the fun part happens. Once one addition unit happened, what we saw previously on the screen, a second can occur. So you have 1 unit and 2 units, and then a third can occur, 1, 2, 3, a fourth, and so on and so on. And that propagation continues to go and go and go, giving you that overall net reaction. Now there will be eventually a coupling reaction that destroys 2 radicals, right? But it could be either between the other peroxide, or it could even be combining 2 chains, right? So we have a bunch of carbon chains bound together, and yes, chain branching can occur. You can think that this polymerization, this radical mechanism, is going to just cascade and continue to add. Now, highly branched polyethylene forms give us flexible plastics. So if you start having multiple branching, the molecule itself, the polymer, is a little bit more flexible. The unbranched polyethylene is more brittle, like the top of the plastic container, right? So you can kind of see the 2 different styles or 2 different feels of the polymer, the plastic itself, and it's based off of what the structure of the polymerization actually looks like. Just to present some of the real life applications, propylene, or 1 propene, 3 carbons with an alkene. That monomer can be used to make a polymer that is used in carpet fibers or appliances, car tires too. Styrene, it's the carbon-carbon double bond with a phenyl or a benzene ring attached to it. Polystyrene is used for styrofoam, televisions, radios, all sorts of things. The ones that are maybe a little bit more in the forefront of your life, PVC pipes, CDs, garden hoses, all of those use vinyl chloride, and then tetrafluoroethylene. With all those 4 fluorines on there, that polymerization reaction makes Teflon for nonstick coating for fry pans. That's all I have for our real life applications. I hope that can kind of bridge the gap between where do we use these radical reactions in real life, and give you some aspects of radical mechanisms happening in your own home.